Okay, this video is on determining the concentration of ions, or the molarity of ions, in a solution after the reaction has occurred. Okay, so the first part of this is all old, and writing an equation, who's the precipitate, who's limiting, that kind of stuff. So you're probably more than capable of doing this part on your own. I would advise that you do that, pause this video, do A through D by yourself, and then, fast forward through it and make sure that your answers match mine. And then part E is the big discussion here. How do I calculate the molarity of each ion in the solution after the reaction has happened? Okay, so here we go. My equation would be KOH plus the nickel sulfate, both being aqueous, of course, making K2SO4, who is definitely not the precipitate, and then nickel hydroxide, who then by process of elimination must be the precipitate. Of course, I have to balance this, and yes, I think that's it. Okay, what precipitate forms? Well, that's the NiOH2. Identify the limiting. Okay, so this is where I need to do my math, so I'm just going to come up here and do it. So let's see, moles of KOH, molarity times liters. So 0.2 times 0.1, 0.02 moles. I'm dropping my sig figs only because they're zeros and I can put them back on later. So I can write a sequence with that number, and then my moles of the nickel sulfate. 0.15 times 0.2, 0.03. So I can write a second sequence with that number. Of course, with my two sequences, I can figure out who's limiting. The numbers for this work out pretty nicely. They're easy to work with. And from here, I know that KOH is going to be my limiting reactant because I had 0.02 moles and I used 0.02. So then NiSO4 is in excess. Grams of the precipitate, of course, will be the moles. So 0.01 moles. I almost wrote grams. And then I just need a molar mass. I do not know that off the top of my head. Nickel. Okay, so hold on, sorry. I did the calculation wrong, just like you guys sometimes do. So it's easy to mess that up. 92.706, making the grams of my precipitate let's see, to 3 sig figs, 0.927 grams. Okay, and like we said before, that's all old information, just regular stoic, limiting in excess, calculating how much precipitate. That nothing there should be startling and new to us. However, this next part is. So I'm actually going to delete like B through D because I don't really need them, and I want this space with the reaction so that I can have lots of room here. So bear with me for 1 second. Okay. All right, and then I'm even going to go ahead and delete this. Okay, so, but I know that part E is asking me for the molarity of each ion in the beaker when the reaction is over. So the first thing I'm going to do is draw the beaker. Bet you couldn't have guessed. Okay, and I want to have a discussion about who's in this beaker, because before we can answer the question, we have to know who we're calculating molarities for. So the first thing that is evident that is in this beaker are my two products, right? My one product is the K2SO4. My other one is the nickel 2 hydroxide. The nickel 2 hydroxide is a precipitate. So given enough time, it should sink to the bottom and it will remain like this because it is a precipitate and no ionization occurs. However, the K2SO4 is aqueous, and so we now know that it doesn't exist as K2SO4. It instead goes through ionization. It's a strong electrolyte, and so the whole thing will ionize. Think about your ratios here. For 1 K2SO4, I should get 2 K pluses and 1 SO4. If you're not convinced of that, you can always write it out. But most of us can see that in your head and in our head. If you need to write it out, that's totally fine. Okay, and a lot of people will stop there, right? But of course, we now know we're on guard to not forget about the excess. We know this was a limiting problem, and we know that there's excess in this container. Okay, the excess is in nickel sulfate, right? And just like the potassium sulfate, it also is a strong electrolyte, and so it ionizes. And this time, it's a 1-to-1 ratio. So I have some nickel plus 2, and I have some more sulfate. Okay, so this question is asking me for the molarity of each ion in the container. So I have 3. I have K plus, I have Ni plus 2, and I have SO4 minus 2. So I'm going to find the molarity of the K plus, the molarity of the nickel plus 2, and the molarity of the SO4 minus 2. That's the goal of this question. We know that molarity is calculated with moles and liters. But we can be more specific, just like we have before. In the first one, if I'm looking for the molarity of the K plus ion, then all I want are the moles of the K plus ion. And we must have a conversation in just a minute about where does the K plus come from. Same thing with the nickel plus 2. If I want molarity of just nickel plus 2, then I need moles of just nickel plus 2. And the same with the sulfate. The liters, as we've encountered before, are fairly easy to calculate. Okay, if you go back up to your original problem, it says we mixed 100 mils with 200 mils, right? And remember that volume is additive. So my total volume in this container is 300 mils or 0.3 liters. And the volume is all the same, right? Convince yourself that the volume is all the same because all of the ions are in the same beaker of water. So yes, the volume of the solution will be the same for all 3. The moles, however, should be different. So when we go to find the moles, we have to have a conversation with ourselves about where did each of these ions come from, and then use our numbers in our sequences to help us come up with those mole values. So let's do K plus first. K plus is in this beaker, right? And so the first thing you need to convince yourself of is where did the K plus come from? Well, it came from this, okay, the K2SO4. And only from the K2SO4. Some people might be inclined to say it came from the KOH. No, it didn't. KOH is limiting and it is gone. So there is one source of K plus and it is from the K2SO4. Now, we know a little bit about K2SO4. One, we know it ionizes according to this reaction. But we also know that I ended up with 0.01 moles of it. So this is where we think about the whole thing versus the ion. And it's good that we wrote this reaction out because it'll let us see it. If I have 0.01 moles of the K2SO4, I have twice as much K because it's a 2-to-1 ratio. You can also see that from the formula if you hadn't written this ionization reaction out. For that matter, I might as well complete the sequence, which is going to be the same as the K2SO4 for the SO4 because it's a 1-to-1 relationship. That's the only source of the potassium ion from or in this solution. So I now know that the moles of potassium are just 0.02. Do the math, round to sig figs, and my answer is 0.0667 molar, or moles per liter, whichever you prefer. The nickel plus 2 is in a similar fashion, right? Again, ask yourself, where does the nickel come from? Okay, it doesn't come from the precipitate. Remember, the precipitate is not ionized, so there is no source of nickel plus 2 from here. The nickel plus 2 comes only from the NiSO4, who is in fact in excess. And this is where students can make a small mistake. Most of the time, students will say, oh, I have 0.01 moles of the nickel sulfate. No, because that's what we used. The excess is what's left over. So let me change my color so we can see it. The nickel sulfate, I started with 0.03 moles, and I used 0.01 moles. So I have 0.02 moles left over. That is what's in the container, not what I used. Okay, so that's one point of misunderstanding sometimes. I can do the same thing and write my ionization sequence with my 0.02. And here's my reaction. I already did it. And this time it's a 1-to-1 relationship, all of them. So they're all 0.02. So nickel, I have 0.02 moles of it. Again, it comes from nowhere else other than the excess. And so my moles of nickel actually are equivalent to my moles of potassium. And so my molarities are the same. We save the SO4 for last. It's the hardest one to do. And if you're following along, you probably see this. When you ask yourself where the sulfate came from, the answer is it came from two places. Sulfate came from the K2SO4, which ionized. And look, we've already done the work. Here it is. And sulfate came from the excess in ISO4, which also ionized. And again, look, we've already done the work. So it has two sources, which means I can add those moles together. 0.02 and 0.01 are 0.03, which gives me a molarity of 0.100, technically for sig figs, of my SO4. Okay, and that is how you have to proceed if you're being asked about the molarity of your ions in the solution. The first thing is to consider who is in the solution, and then it's a game of thinking about, well, where did each of them come from? And I think as long as you can do that, you have all the numbers that you need from writing your sequence. You can work this through step by step. I always like to ask students, of course, if this solution would conduct electricity, and the answer should be a resounding yes, because there are lots of ions in that solution.